Yesterday we learned about the wire grasp rule, which is the rule that allows us to find the magnetic field produced by a moving charge. We reviewed that a few minutes ago. It says stick your thumb in the direction of the moving charge, bend your fingers. How much? Doesn't matter. Your fingers will point automatically in the direction of the magnetic field that's produced by that moving charge. Okay? Not simple, but not too bad. We're going to do another rule today, which is also solenoids. Does anybody know what a solenoid is? Yep. No, not exactly. A solenoid is a coil of wire. When you have wire wrapped around something, a conductor wrapped around something. When you have a solenoid or a coil of wire, you can find the polarity of that solenoid. The wire, if it has an electric current going through it, generates a magnetic field according to the wire grasp rule. But because you have loops looping around, it's easier to find the polarity of that solenoid by and the fingers are going to point in the direction of the moving charges, which is effectively here the direction of the electric current. So in one rule, it's thumb, current, fingers, field. The next rule is thumb, field, fingers, current. Exactly the opposite. You can draw this picture or not. I don't really care. In the end, it illustrates what we're talking about here. If I have an electric current in the direction indicated, an electron current, by the way, in the direction indicated by the green arrows here, you can see that my fingers are pointing in that direction. They're going with that electric current. And my thumb is going to point in the direction of the magnetic field. You can see that the thumb is consistent with the direction of the magnetic field there. Just recognize that it's the magnetic field inside that coil. If the magnetic field inside that coil is pointing to the right, then that means that this would be the north pole and this would be the south pole. Wait a second. Didn't we say magnetic field points from north to south? Magnetic field points from north to south outside. Here we're finding the magnetic field, Mason, inside. Good. So the magnetic field is going to point from south to north here. We'll do a bunch of examples of this, so don't worry if you're thinking that doesn't make a lot of sense to me yet. It will make sense to you, I promise. I'm going to draw one here now that has a coil that has a piece of steel inside it, or some kind of ferromagnetic material inside it. Recognize that when we do this, we don't really need that ferromagnetic material inside it. This coil of wire will develop a polarity, a north pole and a south pole, even without that core in there, even without that ferromagnetic material. But A, it's going to be stronger with the core in there because it's going to be stored and it's going to last longer. If I don't have a core in there, it's going to disappear instantly whenever I turn the electric current off. So usually we have a core in there that's made out of a ferromagnetic material, but if there's not, we're still going to follow the exact same coil rule in order to determine the polarity. It's just the lasting effect and the strength is going to be different. There's the core, the piece of steel. It's ferromagnetic, but it's not magnetized. Here's my wire wrapped around it. Here's a battery attached to it. Do you know which end of this battery is positive, which end is negative? The short side of the battery is negative, the long side is positive. Here's how I remember that myself. The positive, the symbol for positive, has a longer vertical line than the symbol for negative. In fact, the symbol for negative doesn't have a vertical line. So I remember that the positive end of the battery is the side of the battery that has the longer vertical line, right? Just like the symbol for positive has the longer vertical line. This is the positive side, this is the negative side. Now, if we're looking at electron current here, electron current, the flow of negative charges, then electron current will flow this way. Out of the negative terminal of the battery, around here, up in the front, and it keeps going down in the back, and it ends up going around to its source again. Does that make sense? Goes clockwise. Here's what I want you to do. Question?
I was just wondering, when the charge goes back into the battery, does it get recycled, or does the battery need to recharge?
Well, it's not necessarily specific electrons. Electrons get energized from the chemicals, like the chemical potential energy or whatever it is that's supplying it, right? The solar energy or whatever it is that's supplying it. So the important part of it is not so much this electron versus that electron. The important part of it is the potential difference, the energy that's generated in there, that pumps the electrons, that pump an electron. Okay? All right, so take the little craft that you made a few minutes ago, your little solenoid with the word front, and look at it. Look at the word front. I'm not looking at the word front because I want you to see on my solenoid here what you're supposed to see on your own. Okay, you're not doing it as if you're me, you're doing it, I'm doing it from your perspective. So you're looking at the word front on mine, and you're looking at the word front on your solenoid. Got it? I don't want to see anybody's solenoid turned around like this so that I can see the word front. I don't want to see any words. Okay, I just want to see blank solenoids. Everybody should be looking at their own and mine that has the word front on it. Now, the front of this piece of paper represents the front of a solenoid. Got it? You're looking at the front. You're always looking at the front. Now what I want you to do is, remember that hand rule, that coil rule, said fingers go in the direction of the current, thumb in the direction of the magnetic field, opposite to the wire grasper, right? So I want to stick my fingers on the word front, always. My fingertips, where my nails are, on the word front. Which way should they be pointing on the word front? Look at this. Which way should they be pointing on the word front? Up. So stick your fingertips on the word front. Don't do this. Don't do like any kind of crazy thing. Just put your fingertips like this on the word front, just like this. Which way does my thumb point? Which way does my thumb point? When I remember, fingers and thumb have to be 90 to each other, right? Right angles. Which way does my thumb point when my fingers are up, pointing up on the word front? No. You're using your right hand. It's pointing to the right. Does that make sense? So I'm going to say the magnetic field here is to the right. That means that this would be north or south. South, because magnetic field inside points from north to south. That would be the polarity of that electromagnet. Now, you could extend those lines around like this to draw the magnetic field outside of the solenoid, although it's not usually necessary to do that. Usually we're looking for just the inside there, from south to north. Now, let me do this one a little bit differently. There's the core again. I'm going to draw the wire in the same way. Batteries set up exactly the same with a negative terminal and a positive terminal. This time, I'm going to use conventional current. Conventional current will go this way. Up in the back, down in the front. Up in the back, down in the front. It's not really protons that move around here, but I just want to demonstrate for you that if you do get a question involving conventional current, it doesn't matter as long as you're consistent. Everybody take your solenoid again. Put your right hand, because it's conventional current, right? Right hand, the right finger's on the word front. Fingertips on the word front. Bend your fingers around. Thumb points to the right. Okay, you got to put your fingers on the word front, right? Okay, your fingertips go on the word front, not on the other side, on the word front. If my fingertips go on the word front, the magnetic field is going to point this way. This is a south, this is a north, and it would loop around this way. Do you see that? It doesn't matter whether I'm using electron current or conventional current. It gives us the same result in the way you look at it, as long as you're consistent, as long as we're consistent. Let's do a couple more examples here. Let's do another example here. This time, let's have a coil like this. Or sorry, let's have a solenoid like this. Let's go electron current. And we're looping it around like this. And let's make our battery like this. Which end of the battery is positive and negative? Top end is positive, bottom end is negative. If we're talking about electron current, it's going to go around like this, to the right in the front, and then it's going to loop around to the left in the back, right? It's going to loop around like this. Make sense? Orient your solenoid like this is oriented, vertically. That's not a big deal, but you're still looking at the word front. Got it? You're not looking at the word front. Look at the word front. Yeah, we're talking about electron current. You can see that's electron current because we've got it leaving the negative end. Even if it doesn't say electron current in the question, if they have it drawn like this, leaving the negative end, it's the flow of negative electron current. Okay? So, we're using our left hand for this. Our left hand, you're looking at the word front. I'm not, because I want you to see the word front on mine, right? You're looking at the word front. Your left hand, the fingers of your left hand are going to point to the right on the word front. Like this? No, my fingers are pointing to the left. Like this? No. Okay, my fingers aren't on the word front. Like this, my fingertips are on the word front and they're pointing to the right. Got it? Which way is my thumb pointing? Down. So the magnetic field here would be down like this. That's inside the coil, which means that this is going to be which terminal? Which pole, the north or south? Going to be south. This one's going to be north. We could extend that around and go from north to south outside, but it's not necessary for that question. Let's try another one. Here's another horizontal one. This time, let's make our let's make it like this. Okay, which end is positive, which end is negative? This side is good. If we're talking about electron current, it would go around like this, up in the front, down in the back, and around like this. If we were talking about conventional current, we'd draw it the other way, and that's not a big deal. We just use our other hand. It would give us the same answer here. I'm choosing to use electron current here. Everybody should be looking at the word front now on their handmade, arts and crafty solenoid. And everybody should take your left hand, and your left hand fingers should point on the word front. They should point up. Don't do this, although that would actually give you the right answer. Don't do that. Put your fingertips on the word front. Make sure they're pointing up on the word front. Which way is my thumb pointing? When I go to bend my hand around, my thumb points to the right. Make sense? Make sure your thumb and your fingers are 90. Fingers on the word front, thumb points towards the right. Look at your thumb, pointing to the right. So that's going to give us which pole? This is south, this is north. Good? Okay, let's do another one that's a little bit different, but you're still going to be able to do. Actually, let's make this vertical. There's a battery over here, but you're not given the polarity of the battery. There's a current flowing through this wire, but you're not told which direction the current is flowing. This is a non-magnetized ferromagnetic material that becomes magnetized such that this becomes the north pole and this becomes a south pole. Understand what I've got set up here. This is not a magnet that we've put inside a coil of wire. This is a ferromagnetic material that we put inside a coil of wire. There's a current going through it which produces this magnet. It makes this magnet. Got it? We want to find the polarity of the battery over here. This is just a little algebra, right? Using a hand rule. We're going to rearrange the hand rule. Instead of fingers go this way, see which way my thumb points, we're going to say thumb goes this way, see which way my fingers point. Question? That doesn't matter. It doesn't matter. What do you want to use? Conventional electron current. Okay, let's use electron current then. Okay, doesn't make any difference. I'll show you how it doesn't make any difference in a second. Okay, let me just make a copy of this actually. So you said you want to do electron current, right? Okay, let's do electron current. First thing we say is, we know the direction of the magnetic field that's been generated here. It's from south to north. Inside the coil, it's from south to north. Outside, it would be north to south, but inside, it's from south to north. Take your coil that you made a few minutes ago with your rolled up piece of paper. Look at the word front. Don't look at anything else, just the word front. Usually we say my fingers are pointing in a certain direction, which is my thumb point. This time I say my left thumb points down. If my left thumb points down, and then I put my fingertips on the word front, not wrapped all the way around like this, put your fingertips on the word front. Which way are my fingertips pointing? To the right. My fingertips are pointing to the right. See that? No, your thumb is pointing down, your fingertips are pointing this way. Got it? It's pointed to the right. So let's draw this now to the right. If it's going to the right, then it loops around like this. What's the polarity of this battery? Which end is positive, which end is negative? This side is negative, and this side is good. Done. Now, Mason, you asked the question, and it was a good question. Is it electron current or is it conventional current? And I said my answer to that question was doesn't matter. Let's do conventional current now. Let's do conventional current now. Just hold on. If we do conventional current, we still have magnetic field going from south to north, right? Independent of that. Magnetic field inside goes from south to north. Now, we're going to use our right hand because you're doing conventional current, okay? Right hand conventional current. Your right thumb points down again. My right fingers on the word front point which way? Which way are they pointing? To the left. That means my current, my conventional current is going to go this way. If my conventional current goes this way, then which end is positive, which end is negative of your battery? Top one is negative. Bottom one is positive. Doesn't make any difference whether you use electron current or conventional current as long as you're consistent through the question. Does that make sense, Mason?
Yeah, I need the battery to be the same.
Okay, but that's the point, right? Is to get the battery, right? That was the question. Let's get the battery, right?
Wouldn't it be pretty easy to mess up, and since your fingers are pointing left, couldn't you write it at the bar that it's going left,
So I don't understand your question exactly.
like where it's coming kind of out of the north, couldn't you write left there?
Where what's coming out of the north?
Like the blue line.
The wire?
Yeah.
Couldn't I do what?
Like if you put it like this and your fingers are pointing left, wouldn't it be easy to make the mistake and draw the arrows pointing left?
Oh, sure, it would be easy to make the mistake, but it would be a mistake because that wire is coming behind.
So it's the line.
Yeah, because that's why you're putting your fingers on the word front, right? That's why I am insisting that you put your fingers on the word front. When you put your fingers to the left, in this case, on the word front, then the current is to the left in the front, not to the left in the back, to the left in the front. You asked the question, wouldn't it be easy to make that mistake? Absolutely. You're absolutely correct about that. It would be easy to make that mistake, but it's a mistake. Your fingers are on the word front. The current is, whatever direction you find those fingers are pointing, is in the front.
I just wanted to know how it
Yeah, the simple answer to that question, I don't mean to be
Oh,
Too simplistic about it is just be careful, right? Make sure that you're looking at the front. Always start with the front. Always work with the front, and then the back will just fall into place, right? I went to the front, to the left, 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 and then kind of loops around and goes to the right in the back by default after we figure out the front. Good? Okay, I'm going to draw a couple on the board here for you guys to do yourselves. And if you have trouble with it, you can ask me. I can help you with it. I don't expect you to be perfect at this yet, to have mastered this yet. Don't be afraid to ask those questions. Okay, here's the first one. What should you use here, Mason? Electron current or conventional current? Doesn't really matter. If the current is labeled, then you should use whatever they label, right? If I label the current this way, that's electron current, and you should use electron current. But if it's not labeled, do whatever you want. Just be consistent. I'm going to label that there as electron current. The second one I'm going to give you, by the way, you're trying to find the magnetic field there, right? The magnetic field inside. The second one that I'm going to give you is going to look like this. Oops. Let's fix that up a little bit here. Sometimes it's kind of a pain to draw these things. We're looking for the battery here. But in order to find the polarity of the battery, you have to know what end is north and what end is south. So I'm going to make this north, and I'm going to make this south. Now, what should you use for this one? Conventional current, electron current. I'm not specifying there, right? If I don't specify, it doesn't really matter, right? I would personally go with electron current, but it doesn't make any difference as long as you are consistent. Yep. Yep. In the first one, we have a current here. If we're dealing with electron current, that goes up in the front. Okay, it goes up in the front, curls around down in the back, up in the front, down in the back, and so on. Goes around like this. I'm going to take my solenoid. I want my fingers, not like the ends of my fingers, not the point where my ring is, not the point where my knuckle is. I want my fingertips to point on the word front, up. Now, some of you notice that like you don't actually really have to bend your hand around there. Okay, technically you do, but in the end, you can still get the direction of your thumb pointing to the right. That means the magnetic field points to the right. This is the south pole. This is the north pole. Now, in the second one, it doesn't really matter whether you use electron current or conventional current. Question?
What does B with the...
This just means the magnetic field. We can't find the strength of it. We don't know how to find the strength of it. I'm just asking you to find the direction of the magnetic field. Okay. Now, the second one, we know this time, first of all, that it's vertical. Second of all, that the top of it is north. And third of all, that my thumb has to point to the north inside the coil. So my thumb is pointed to the north. You can see that right now, right? Where am I? Oh, I don't want this because my fingertips are not on the word front. I want my thumb to point to the north and my fingertips to be on the word front. Which way are my fingertips pointing? If they're on the word front and my thumb is pointing towards the north. Which way are my fingertips pointing? To the left. So my current here, that is, I'm using my left hand, right? So the electron current points to the left, in the front, because I put my fingers on the word front. And then they go around here like this. What's the battery look like? Well, what would this be, positive or negative? Positive. This would be... Does that kind of make sense?